Welcome back. Hope you're doing well. Now that we have learned some of the basic integral laws and the construction of the Riemann integral in our previous lesson, now it's time to get to something that is very fundamental to our learning in this unit. Indeed, talking about the integral using the fundamental theorem of calculus feels like it's kind of missing something, right? Like it feels like there's a lot of machinery going around, but I know that's not how the integral works because I know that it essentially reverses the direction of the derivative. Indeed, last time we discussed that essentially the integral is like the inverse operator of the differential operator for specific classes of functions. And we're going to be very specific about what types of functions work nicely for that here. So that's what we're going to be covering in today's lecture. And as we continue on, we'll also talk about the indefinite integral, namely the one whose derivative is going to give you the function that you're integrating. So let's go ahead and see that here by starting with constructing a function which has a variable as its limit. For example, let's say that a function is defined on an interval from a to b, and let's fix that point a as one of our limits for this integral that we're about to take. Now let's let the right-hand part of this vary a little bit. Let's make this our variable so that our limit of the integral that we are taking is from a to x being our variable here for this function f. We're going to call this function capital F, and that's going to be the kind of the stemming point for our little antiderivative type function. Well, once we construct this, we can start saying a few things that are neat about it. One thing is that you can show the function f is well-defined and continuous, going from a to b. One thing that helps us here is, you remember one of our previous theorems said that an integrable function is bounded. So if I want to take a look to see, okay, well, what happens if I make f of x minus f of c and look at this value when x and c are very close together? Well, the idea is that these two things should be very close together, right? And that's because what? What is this value going to be? This is going to be equal to the integral from c to x of f of t dt. And because of this, we have a very small interval for us to integrate. So going from c to x, if we're assuming that maybe x minus c is less than delta for something like this. And f is bounded. So the maximum possible amount that this area can be is going to be bounded above or below, depending on if it's above or below the x-axis. And so this value right here should be a rather small amount. In general, we should be able to get that in b in terms of epsilon. And indeed, we can always do this whenever our function f is integrable. Now, theorem 2 says if f itself is also continuous, the thing that you're trying to integrate at a particular point, then you can actually find the derivative at x, right? So you can take this formula and actually divide it by x minus c and get something nice out of this. The idea here is that, and this is the gist of this proof, is that you're essentially, this value is going to be like an average value of your function over the interval going from c to x. Well, if you keep making that interval smaller and smaller, you just get the value at that point. That's what you end up getting. Now, that's only possible if you don't have anything like a jump discontinuity or something like this. So we do ask our function to be continuous at this point in order for this to work. So that is an important condition there. Now, one of the ways that we could start seeing the integral become useful, and sometimes this is something that we need, is to try and evaluate the integrals of the absolute value of a function f. So what we're doing here is we're composing two functions. We have the function f, right? Whatever this ends up being. So for example, we could think of this as x cubed, and then we're composing it through the absolute value function. So that what ends up happening, if it gives you negative values like this one does whenever x is less than 0, then that ends up going to end up giving you the positive values there instead. Well, one thing that we might think about is that how does this compare to the normal integral of f, the one without the absolute values in it? Well, this is what this lemma is useful for. We're going to use this to say that the absolute value of the integral is less than or equal to the integral of the absolute value for any integrable function f. By the way, part of this statement also is saying that the absolute value of f is itself an integrable function. And we'll go through and see a little bit as to why that is actually true. Well, one, we have something that is the composition of the function f integrable with a continuous function absolute value of x. Well, these are both a continuous function is going to be integrable. So this is a composition of integrable functions. So the absolute value of f is integrable on this interval. Now, also, we see that f is going to be in between on the right-hand side. It's going to be at least less than or equal to absolute value of f of x, and it's going to be greater than or equal to the negative absolute value of f of x. Think of this as like kind of like the opposite of what absolute value likes to be. Absolute value gives you all the positive values. This can only give you negative values. So this bounds it beneath. Then the comparison test for integrals gives us everything else that we would like, because now we see that the integral of f of x dx is going to be in between these two values. Well, what does that mean? If I take an absolute value of the integral from a to b of f of x dx, well, then this absolute value is on the left going to be bounded below by this and bounded above by this for this function. So this whole thing is going to be less than or equal to the absolute value of f of x dx, which is exactly what I'm looking for. All right, so this is a neat little lemma that tells us that we can connect things coming from a function to the absolute value of that function. And that leads us here to this first part of the fundamental theorem of calculus. You might recognize this function big F that we have here given in the theorem, which says if we have a function that is continuous on an entire interval, where before we had in our previous discussion, we had only the function being continuous potentially at a specific point. Here it is continuous everywhere on this interval. Then the function given by big F, the one that we had discussed before, is continuously differentiable on A. Recall, that means that it has a derivative and that that derivative is continuous. Moreover, what that derivative is, F prime, is going to be F. So the way we're going to get that this is continuously differentiable is going to come up straight out of this statement, because F itself is going to be continuous on this interval. Well, since f is continuous, it has to be integrable. And as we have proven earlier, the integrable of f implies that the function f is well-defined and continuous on the interval going from a to b. Moreover, f prime equals f whenever f is continuous at the point x. We've just already done this at points, so now we're just saying this to be true for the integral. Therefore, the continuity of f implies that f prime equals f. In particular, f is continuously differentiable. And that's all we really need to show. It's kind of neat that we're sweeping a couple of details under the rug, but not really that much, right? The only thing that I was trying to maybe hand wave a little bit is that this kind of gives us an average value of the function, and maybe we could be a little more specific about how the continuity of f at a specific point helps us out with that. But at the end of the day, we've shown everything that we need to show. This is the fundamental theorem of calculus. Now that we've built up all of our machinery, this is really not that bad. And indeed, the second part is also going to be a kind of a straightforward argument. Note, first of all, that this one is kind of doing the flip-flop of what we had before. In part one, what we were doing was we were saying, okay, take a function f, which is the integral of this function. Then the derivative of the integral gets us back to the function, right? This one is going to be, as you can see here, the order is switched. This is going to be talking about the integral of the derivative of a function. Here, we're starting with a function that is differentiable, hence its derivative can be taken. Then as long as the derivative f prime is itself integrable on this closed interval, then when you take that integral, it's going to be just f of b minus f of a, right? You're just plugging in final minus initial for this point. Now, note that, first of all, the derivative of f prime need not be continuous. So we're not actually working in the world of continuous differentiable that we were back in part one. So these two are working in slightly different collections of functions here. So the way that we're going to do this is we're going to go back to the machinery of the Riemann sum. So let's consider first a arbitrary partition of the closed interval going from a, b. And let's just go ahead and choose some samples. But let's choose these samples in a particular way. Let's choose these samples inside of each of these partitions here so that the t sub j that you choose for f prime here is going to be, you're able to find it in this way. Now, this equation might look familiar to us because indeed this is the statement of the mean value theorem. The mean value theorem says that finding these t sub j is possible for any part in which you're looking at a function that is continuous on the closed interval and differentiable on the open interval. In this case, the subinterval going from x of j minus 1 to x of j. Well, this function is differentiable on the entire closed interval, so we definitely satisfy those conditions. So finding this t sub j is very possible. Then, now that we found this, we know that the Riemann sum with respect to this partition and this collection of samples gives us something like this. Well, if I look at what that is, this is the sum of f prime of t sub j times x of j minus x of j minus 1. And then I can say, okay, well, in fact, this is the right-hand side of this equality here. Well, so then I can replace it with the left-hand side. And that's exactly what happens right here. I'm now replacing this with a telescoping sum, because if I continue to move up the ranks by this summation in J, then you can see here that if I went to looking instead of at J plus 1, then that's going to be f of x sub j plus 1 minus f of x sub j. In that case, I would have something that cancels. The f of x sub j is going to cancel. So all of the intermediate terms in this similar way are going to be canceling for us. And all that we're left with are the points at the very end and at the very beginning. The one at the end is added, the one at the end beginning is subtracted. F of x of n minus f of x naught. Now, by the definition of partition, this is exactly f of b minus f of a. Now, notice that with this particular partition and this particular sample set, we've now gotten something that does not rely on the partition and does not rely on the samples that we chose. So, because we can find this particular sample for any given partition, we can now just take the norm of p to go to 0. And that's not going to impact what this value is at all. So this gives us that the sums indeed converge to what this is going to be, the integral from a to b of f prime of dt. So this is what is given to us here. Now, with all of this sort of machinery, I think a picture is indeed in order. So let's go ahead and see what it is that we're looking at here. Let's take a generic function here, something like this, y equals v of t, for example. And in this case, we're going to try and think of this in terms of its applications. Let's think of this as like a velocity function. Well, if I do that, then what I'm going to try and do is try and find an area under the curve for this that is particularly small. Maybe I'd start here from some point, so like say this is t0 and this is t sub 1, and begin my partition in this way. Looks like this is frozen for a second. Give me a moment. Okay, we've got it back now. So we have this small little subinterval that we're working with here. Now, finding this area underneath this entire curve, if we went all the way over here to say t sub n, this would involve taking a sum of k values going from 1 to n of t sub k minus t sub k minus 1, that is finding the width of one of these rectangles, and then multiplying it times the height of one of those rectangles. In this case, we're going to assume that our integrals are very small, so that finding these heights is going to be, not rely too much on the sample. In particular, since our functions here are going to be, make sure I'm saying this correctly, are going to be differentiable, or that f prime itself is going to be integrable. We know that these are going to be bounded functions. And because of that, there's not going to be too much variation here with regards to how much can take place with these, at least in these parts in which they are integrable. So we are going to have t sub k minus 1 as the multiplication here, and we're going to multiply this times some v of t sub k star here, t sub k star being some sample points that I am choosing inside of here. So maybe I choose the t sub 1 star that exists right here. Now, if I take a look at that and sum over each of those rectangles, then what I'm getting there is the integral going from a to b of v of t. That is, as long as I take a limit as, say, n goes to infinity, and I'm only looking at partitions as their largest possible subinterval goes towards 0. In fact, maybe that's a better way to write this. I've seen this before. This is a good way I think of writing this. I could take this to be the limit as the norm of p goes towards 0. So now I have this integral to be writing here, the integral from a to b of v of t dt. But there's another way that we know in order to figure out what this integral is equal to, right? This is essentially going through and figuring out a displacement of this velocity. And that's because here we know that there is a formula for figuring out how to write s of t in terms of v of t. And the idea is that if you take the derivative of the displacement function of a particular particle or a certain moving object, then what you get is the velocity function of that particular particle or object. So what we can do instead is say, okay, well, this is going to be this particular displacement that's taking place going from a to b. So another way to find displacement is just to take the displacement formula and do final minus initial, do s of b minus s of a. So this is a very common application that we see of looking with the fundamental theorem of calculus here. So putting everything here together, we get exactly our formula. Using the fact that v is equal to s prime, I can write in, this is the integral from a to b of s prime of t dt, and that this is equal to s of b minus s of a. So this is a very good context for us to understand the fundamental theorem of calculus part 2, is that you can think of it as you're integrating over velocity and you're getting a position function. All right. So this helps us get our handle on what the fundamental theorem of calculus is. But what does it do? The idea is that the fundamental theorem of calculus does most of the work for us whenever we are attempting to find things like indefinite integrals. Indefinite integrals are going to be functions such that the derivative of that function gives you the function in question. So if you're looking at a function that you're given, then a function big F is going to be the indefinite integral whenever f prime, big F prime is equal to little f. And that notation is essentially the function itself, but without the limits a or b inside of that. Now, we can go through and use the fundamental theorem of calculus to show that you get these indefinite integrals, for example, whenever the function f is continuous on your closed interval. So going through and calculating big F of x to be the integral from a to x of little f is going to be perfectly fine, because we just saw from the first part of the fundamental theorem of calculus that this ends up having exactly this property right here. Now, let's suppose that big F is an antiderivative of f. We talking about antiderivative, that's another term for indefinite integral here. If g is another one, let's see how close we can get to uniqueness here. Let's say that, first of all, that we have another antiderivative of f. Well, then g prime is going to equal f prime, because both of these are equal to just the function f on that interval. So what that means is that the derivative of g minus f is going to be equal to 0. So what that means is that g minus f has to be constant, right? You're thinking of something that has a slope of 0 absolutely everywhere. Now, conversely, for any constant c, the function g equals f plus c is also an antiderivative of f. So we've actually gone ahead and classified what we mean by uniqueness in terms of the antiderivative. It is what we might call uniqueness up to a constant, or up to adding or subtracting a constant. Then that means that we can say any antiderivative, if you have one, then you have all of them, because you can classify all of the other antiderivatives by simply adding a constant. So the general indefinite integral gets that little plus c. It gets that as a term in order to say that the indefinite integral is often given as a family of functions, not the function itself. So here you can see that we're defining this to be a function which is the indefinite integral, but we don't mean really we mean that there's multiples of them, because you can add a constant to that and still be called the antiderivative there. So an example of this is that whenever you have x to the alpha, where alpha is not equal to -1, then you can use the fundamental theorem of calculus to say, okay, well, in order for me to try and figure out what this integral formula is going to be, instead of me trying to actually do the Riemann sum for this and then take a limit as the norm of my partitions go to 0, I can instead ask the question, what function, if I take its derivative, gives me x to the alpha? And if I do that, then I can just proceed through and, give some sort of intuitive guesses. If I end up finding a function whose derivative indeed gives me x to the alpha, then I know from my previous slide that I have all of them up to a constant, a sum adding a constant. So x to the alpha plus 1 divided by alpha plus 1 is the correct candidate here. For 1 over x, we know log of absolute value of x is what we're looking for here. And the reason that we know the absolute value of x is important here is that whenever we get that we take a derivative of log of x, what we get is 1 over x only on a specific interval, because here x is only the domain of the logarithm function is only on the open one-sided ray, starting from 0 and going off toward infinity. So what we have to do is find another derivative for the other side. The other side is going to be log of -x, it turns out, because here you would get from that derivative 1 over -x, but then you have a chain rule of multiplying it times -1. So what you get is indeed 1 over x. Putting all of these things together, you get a piecewise function that can be simplified to log of absolute value of x. And of course, we add our plus c. Similar stuff shows us the trigonometric functions here. The integral of sine is negative cosine plus c. The integral of cosine is sine plus c. And that comes from the fact that we've already taken the derivatives of these two functions, so we know how to do all of the rest. Some of this, by the way, comes in thanks to our, no, actually it does not. We can just take the derivative of negative cosine and get that is positive sine. So we're just going through and replacing that. But if we had seen, for example, that the derivative of cosine of x is negative sine, then that's good enough too, because I can say, okay, well, the integral of negative sine is negative the integral of sine, thanks to the fact that we learned last time that the integral is a linear operator. So let's go ahead and see some more functions with this one, like x squared over x minus 1. A couple different ways to do this one. One that ends up being more popular here is to try and divide out what is x squared divided by x minus 1. Can I separate this into multiple different terms? And that's exactly what we can do down here. What we can do is say, let's take x squared and let's subtract 1 and add 1 so that it stays the same fraction. Here, looking at this divisor, I have something that I can divide out and get x plus 1 from. And then the remainder, I'm going to get 1 over x minus 1. So after this division, this gives me a particular domain for this function. I note that this function itself is not defined at x equals 1, so I have to be careful a little bit about what is going to be the space for my domain here. So I'm going to need to be a little careful about that. The way that that tells me, okay, maybe this is going to be a little bit picky here, is that I'm noticing here that I'm having to integrate 1 over x minus 1. Well, how would I integrate that? We know this thanks to something called substitution, that gives us something there. But we can also, of course, just use the fundamental theorem of calculus and test out, what about the log of x minus 1 here? Well, if I take the derivative of log of x minus 1, what I end up getting is 1 over x minus 1 times the derivative of x minus 1, thanks to the chain rule. But that's just exactly what we're looking for, since that derivative is 1. So because of this, we can now say, okay, the integral of 1 over x minus 1 is log of x minus 1. And indeed, whenever x is greater than 1, that's exactly what we have. Now, whenever we are looking at stuff to the left of 1, then we have to be looking at the absolute value of this for the same reason that we were looking at that for the previous one, whenever we were taking the integral of 1 over x. So that's exactly what we have right over here. Now, in general, that can be two different constants. And the reason for that is when trying to integrate x squared over x minus 1, we explicitly cannot integrate over 1. And so in some sense, the constants on one side or the other side of the function don't have to see each other. When I take the derivative of this part, for example, what I end up getting is the function x squared over x minus 1, as long as I'm assuming, of course, that this value right here is going to be positive so that my function is well defined. Same thing down here. Whenever this function log of 1 minus x is well defined, I can take the derivative of this function and get x squared over x minus 1. So these constants don't even really see each other. In fact, we could even say the same thing about log of absolute value of x plus c, because here, indeed, you cannot integrate over x equals 0. So the same sort of principle holds. But that'll do it for us today. We've discussed things like the fundamental theorem of calculus and the indefinite integral, some of the big kind of landmarks of this particular section that we're trying to go through. Next time, we're going to try and see if we can utilize these theorems in very good applications of them so that we can integrate larger classes of functions so we can move forward with that. But that'll do it for me today. Thank you so much. Have a wonderful day.